Hello students, welcome back. Let's resume our discussion in section 4. We completed this problem, the first problem. Now let's go to the next problem here. Okay. Laplace transform method or substitution method, either way it works. We have to do the homogeneous part first, and the homogeneous part, as usual, let me go really quickly. We have R over S and then factor the denominator and decompose by partial fraction. And then what do we have? We take the Laplace inversion. What do you get? YH of t is, from here, we get C1 e to the negative 2t, C2 exponential of negative 2t, but we need another t here. Let me see. Okay, this is right. This is right. We don't have to divide by anything. But then again, you don't really have to care in reality. You can always change these to another character, say k1, k2, if you're unsure about what to divide or not to divide or things like that. They are arbitrary constants anyway. And then the non-homogeneous part, we'll discuss it in a moment. How about the substitution method? Just plug everything in, then you're going to get the characteristic equation. And then solve it, we get s equal to negative 2. So we get these two, e to the negative 2t, and then t times e to the negative 2t, and their linear combinations. Okay, either way, we have the same homogeneous part. How about the non-homogeneous part? If you use the Laplace transform method, here we go. We have these three non-homogeneous terms in the right-hand side. We have 1 e to the negative t, and then e to the negative 2t. So we have sum of these three functions, so we have the sum of these three Laplace transforms. Multiply 1 over q and distribute around. We have blue times 1 over q, red times 1 over q, green times 1 over q, like that. And then use technology to decompose this by partial fraction. Yes, I can use paper and pencil method, but that's rather crazy. I did it this way. And then this is the answer I got. Let's go back. Here we go. Excuse me. Why am I having, oh, okay, I see. This second step here is unnecessary. I don't know why I did this part. I can set it up like this and then take the common denominator and then solve for b1, b2, b3, and b4, and b5, and then set up and solve the system of 5 linear equations, which is absolutely crazy. But if I do that, I'm going to get this one. But no, I'm not going to do that. I'm going to use the technology method. So let's go directly down to this one. Okay, that makes a lot more sense. From here, just take this decomposition by partial fraction. And what do we get? We have, let's see, the homogeneous part, which are the last two terms here. S plus 2, and then s plus 2 squared, which were coming from the homogeneous part, R over Q. And then the others are non-homogeneous parts. 1 over s plus 3 cubed, 1 over 4s, 1 over s plus 1, green, blue, and red, respectively. And then take the Laplace inversions. Homogeneous part, we saw this before, and then the non-homogeneous part. Green becomes green, blue becomes blue, red becomes red. That's all there is. As for how to get these, you can always look up the table, the Laplace table, in page 123 of our textbook. Okay, That's the Laplace transform method. And then, of course, the key technique there was the decomposition by partial fraction using the computer algebra system. Now, what if you do not have computer with you? In that case, you may have to do this. You begin with an educated guess. Let's see, this is a polynomial of degree 0. So we have polynomial of degree 0. And then this one is exponential, so b times exponential. Now this one is tricky. It's not going to be just something times exponential, no, because e to the negative 2t, that part's already covered by the homogeneous part, you see. E to the negative 2t, and then t times e to the negative 2t, both of them are covered by homogeneous. So we have to go one higher. I need c squared times that. And then we have to take the derivative. Okay, here we go. And the second derivative, oh my goodness, but here we go. And then plug everything into the original equation. This, and that, and equal to right-hand side, blue, red, and green. And then take the like terms together, compare the coefficients, set up a system of equations, system of 3 equations with 3 unknowns, a, b, and c. And once you solve it, you're going to get this. And eventually, you're going to get this particular solution. Same particular solution that you saw before. And in the end, oh yes, you have the same solution as before. Okay, if you like this method, you can go ahead and use it. But I don't think anybody likes to do this. In this method here, from here to there, I use technology. But then again, if you don't have technology, then you have to take the like terms here, and then you have system of, did we have 5 unknowns and 5 equations? Or did you have 4 unknowns and 4 equations? You have to do something crazy, possibly crazier than even this one. So there's a trade-off one way or the other. Okay, we went through a problem that is, what can I say, absolutely crazy without technology aid, but with technology aid, perfectly fine. How about the next problem here? It's going to be similar too. With technology aid, pretty much same, no big deal. Without the technology aid, crazy. Let's go ahead with this one. How about the homogeneous part? We get this, and then we have exponential sine and cosine. And then how about the substitution method? Characteristic polynomial can be factored like this, or it cannot be factored, excuse me, it can be transformed into complete square plus square like this. So we have exponential sine and cosine, yes. And then the non-homogeneous part. Let's see, here's the Laplace transform method. Small f to capital F upon taking the Laplace transformation. And then we have capital F times 1 over q. Take the decomposition by partial fraction and we get something crazy, but the majority of that part is just homogeneous part, so I don't care too much about that. Here's what Mathematica spat out. Oh, it's not too bad. It's not bad at all. Only this part is homogeneous, so okay, all right. And the other part we have here. And then you take a Laplace inversion. So homogeneous part, and then the Laplace inversions here, blue and red respectively. Okay, with the technology aid, no problem. And what if you do not have the technology aid? Okay, we begin with these educated guessing. We have polynomial of degree 1, so we need at plus b, a polynomial of degree 1. And then the red part, e to the negative t, so we have something times e to the negative t. None of these coincide with the homogeneous part, because in the homogeneous part, what we have e to the some complex or exponential and sine cosines. So you don't really have to multiply t to the whatever power as we did in part B. So here we go. Take the derivatives, second derivative, and then put those into the original equation, compare the coefficients. We have a system of 3 linear equations. Solve it, and you're going to get these, and put everything together, you get a particular solution. Add them together, we have the general solution of the original non-homogeneous equation. If you don't have technology aid, then you'll probably have to do this. That's where I'm going to stop. How about higher order example? No, never mind. We're going to do those in the next chapter, chapter 4, or lesson 7. Let's see, we have just a little bit of time left, so let me talk about the principle of superposition. It's not really that necessary, but it can be useful in some cases. Now, what if you have several independent terms added together in the right-hand side, the non-homogeneous part? What if you have f1, f2, f3, and so on just added together, kind of like this example here? In that case, you can decompose them into several different non-homogeneous linear ODEs, solve them separately, and add them up, and that's going to be my solution. Basically, according to this principle of superposition, we can do it this way. So, get the first particular solution like this, and the second particular solution like this, and the third particular solution like this. Oops. Like this, and then yp. Yp is going to be sum of these three. y1 plus y2 plus y3. Oops. I clicked the wrong key. Sorry about that. I can do it this way. I didn't do it that way. I did all those three put together and then made this educated guess, blue, red, and green put together, and took the derivative again at the same time, second derivative at the same time, put everything in, and then set up the system of linear equations at the same time and got those three at the same time. Here in this my notebook. But if you separate those into three separate problems and go ahead do that, and then add them up later to find out the particular solution, you can do that too if you want to. I don't know why would anybody want to do that, because it's quite likely the equations will be messier this way, or maybe not. I'm not so sure. I haven't actually tried. But in any case, this one works out too. If you prefer, you can do it that way too. Principle of superposition. Okay, that's the end.